So welcome back, everybody. In this next lecture now, we're going to talk about entanglement. And this is a very useful concept, especially in quantum information and quantum cryptography. And entangled states, if we can say something about them, they are the most non-classical, there are, in fact, many ways of defining what non-classical is, and these are at the root of many quantum mechanical paradoxes. We're going to discuss one of them, or some of them maybe, at least outline. And they are a key resource. Entanglement or entangled states are a key resource for quantum computation and quantum cryptography. This is our main motivation. And one important point here, so please note that nearly all systems that are strongly interacting or interacting even, doesn't need to be strong, become entangled. And all quantum systems in nature are interacting. For instance, think about a system and its environment. Think about an atom and an electromagnetic field. Think about two electrons. So really, you have a lot of interacting systems. And we have already talked about compound states, and we're going to define something related to product states, because we have seen how to construct states in a compound vector space, but we are not quite sure whether they are entangled or not. So that's why we're going to introduce the definition of product states. So we say that a state in the space, which is the compounded space we have looked at so far, A tensor product B is a product state if it can be written as a tensor product. For instance, let's have a look once more at spin 1/2 particles. Which we label A and B as before. And we're going to write a lot of compound states. So let's consider psi1, which is first spin up, second spin up. Let's write psi2, 1 down and 1 up. And let's write psi3, where we have 1 up, the other one up, divided by 1/2, plus up and down, plus these are like this, okay? Plus A down, B up, plus A down, B down. And what we can see is that this is a product. This is a product state, right? Because you can write this as a tensor product. So let me specify this is a product state. This one also. With this one, we're not so sure, but you can actually rewrite it as something like this. So if you can do it, you have here one state vector in subspace A, one state vector in subspace B. Call this, if you are struggling, phi A, phi B. And you can see that this would be like 1/2, not normalizing. So it's also product state. Which actually will mean that these states are not entangled. So an entangled state is a state that cannot be written in tensor product form. So for instance, psi 4, 1 square root of 2 A tensor product B plus A down tensor product B down. You are not going to be able to write this in tensor product form, which means, if you think about it, and this is an important consequence, you are not going to be able to say that you have one state vector for system A and one state vector for system B. Meaning that this state describes both particles, so you cannot disentangle them. And it's important to bear in mind this separate, because it means that you would be able to disentangle them. For instance, have a look at these guys. Here, I can say particle A has a spin up, particle B has a spin up, particle A has a spin up, spin down, sorry, particle B has a spin up. Here I can say particle A is in this coherent superposition, particle B is in this other coherent superposition. So I can clearly write down separate state spaces and state vectors for system A and for system B. But here, how would you do that? How would you separate it? You cannot factorize it. So what does this mean? And this is when we have entanglement. We can, for instance, consider an operator now, and we're going to have a look at it in more detail. So in application, or how, let's say we want to perform a measurement. So we want to compute SZ. So these are, for instance, 2 electrons. Okay, assumptions. We would like to perform a measurement. And the particles given above are, for instance, electrons. So how do we do it? So we're going to have, then let's take this operator SZ, which is acting on the electron 1, or if you want, it's acting on A. And let's consider 1 SZ. So if you apply this, you're going to measure the Z component of the spin. And this is acting in the state space, sorry, B. Okay. And what we're going to do is, let's apply these to psi 4. So applied to psi 4. Okay, if you do that, psi 4 was this coherence position here, which we're going to copy and I'm going to paste. And we want to apply this, we want to perform this measurement on the state. So what kind of results can you have? Either both spins are up, which means that the state of the system collapsed. To up A, up B, or both are down. So meaning that the state of the system collapsed to down A, down B. Now, after the measurement, there is, so this is something that's after the measurement was performed, immediately afterwards, that's what we have. And there is a 50-50 chance of getting either outcome. Now, this is what we call global correlation, but some kind of local randomness, because we have seen that the particles are correlated, but the result that you can have is 50-50 up or 50-50 down. And now the question that was posed, in fact, by Einstein, Podolsky, Rosen was the following. If you know for sure, okay, we know both electrons are up and both are down, does this mean that information transferred from one spin to the other is faster than the speed of light? So this is the question that they pose. And this is actually quite deep, because that we know, we perform the measurement, we don't know where the electrons are. One spin is up. If one spin is up, the other is up. If one is down, the other is up. Is down. So does this mean that information from one spin to the other is transmitted faster than the speed of light. If this is the case, this is contradicting special relativity. So this would mean contradiction with special relativity. Now, this is tricky, right? And that's what we call global correlation, because you can see that one spin is affecting the other, but there's some local randomness because there's 50-50 chance of getting either result, up or down. So what would a person do to resolve this? Well, we need somehow to get rid of the information from system A. So what can we do? And what we need to ask is, how would we resolve this? So what would, and this is going to be my next question, what would someone, a physicist, measuring system BC, what do they see? We don't know. So what is the best description that we have without the information from A? Let's think about it. And we have seen. So what can we do? Well, we're going to describe this probabilistic ensemble using what we call by the reduced density matrix one half of system B. Now, we haven't talked about it. We talked about density matrices, and we said density matrices are when you need to somehow incorporate some kind of classical randomness that you don't know, or some information that you don't know. And in this case, what would happen is, if you have no information about A, but the states are still entangled, you need somehow to account this and take this into consideration. And these are concepts that we are going to see. Reduced density matrix, and this will be done then for system B. So there is no change in spin due to the measurements in A when you got rid of all these elements from A, but there was loss of correlation. So no change in spin due to measurements in A, but there was loss of correlation. So what we mean by that? You found a way, and this is some method that we're going to see, to get rid of the correlation that you would have in the system, but you need to consider that at the beginning you are dealing with an entangled state that you cannot factorize. And if you don't have any information about system A, there are ways of taking this into consideration involving density matrices. And the same arguments can be applied for measurements of other operators. And this is an important point. For instance, Sx or Sy, the same arguments can be applied for measurements of Sx or Xy if you wish, whose eigenstates are x plus, so spin plus in direction x, 1 square root of 2, spin up plus spin down in the z direction, which is what we considered before, and x minus 1 square root of 2 spin up in the z direction minus spin down. And what we would have here, we can construct again an entangled state. And this would be 1 square root of 2 x plus a x plus b plus x minus a tensor product with x minus b. So it's pretty much the same as what we had before, but now we're considering that the spins are in the x direction. So you have this and you have that. Up, up, down, down, and you apply an operator Sx, either working on one space or the other. And if you calculate a reduced density matrix, I know this is still a bit mysterious to you guys, but we're going to talk about it. A reduced density matrix or density operator, if you want, is going to be 1/2 x plus x plus plus x minus x minus. You see, because you couldn't write this as a simple projector, you can already see this is not what we call a pure state. And this would be what you get for B. So you have B, 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 B. Outside I put B. So it's pretty much the same results regardless of the basis chosen, which should be because space shouldn't depend on what coordinate you take, or the physics of the problem shouldn't depend on the coordinates that you take. And to understand this, we are going to have a look at density matrices for compound systems. So so far we have not understood what I've been talking about. Okay, you say you can write reduced density matrices. So we have here a few questions. Namely, what do I mean by reduced density matrices? What are these things? Why and how can we use them? Pay attention to the arguments. The arguments were the following: that you had two particles that were entangled at the very beginning, and we wanted to know what would an observer just looking at particle B measure, but we had no way of disentangling this or writing as a tensor product this compound state, because they were entangled. So it's not that you say, this is acting on B and this is acting on A. So we had to find ways of removing this correlation, removing this information. And this is actually related to this concept, which we're going to see next. So the next topic which we are going to deal with here are reduced density matrices.